Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. In this video, it is finally time to talk about meshing in Autodesk Robot. Now this is a very important issue because meshing usually affects the accuracy of your results and thus should be taken care of when you design or basically model in your Autodesk Robot. Now, to truth to be said, not many people do actually pay attention to the mesh because Autodesk Robot has a fantastic mesher. But I will just draw attention to some of the things that you should keep in mind when you want to produce a mesh. So first of all, I will make me a structure that is basically 20 meters or 15 meters by 12 meters of structures. This is a very simple structure just because I want to get the ball running. So there we go. In the z-axis, I will just leave it as is. I don't care now. And I'll go to view. Now, first of all, I'm gonna do me some quick columns. Once again, my focus here is not on basically the structure modeling. However, I'm just gonna take a look on the mesh. So I'm just making me some columns here. Now, this is a perfectly symmetric structure, and I think the columns, I think I messed up. And my point here is that the column should have the same forces. So I'll go select me a plate like this. I'll go, of course, select me like, I don't know, a thickness something. Let me just check. A thickness 200 concrete, for example. Is it thickness 200? Yes, it is. It's a rectangle. It's not a curtain wall. And I'll just basically draw me my thing here. So I have it now. I create me a dead load. This is something that was explained before. Please refer to the Slab series and even the beginner's guide on Autodesk Robot. Anyway, I'll just basically go to loads, load table, because I want to remove the self-weight, because I want to make predictions easier. I'll add me a load. The load is going to be, I don't know, 10 maybe, something. You can, of course, calculate loads, but today it's not about design and load, it's about meshing. So let's first of all do a blind analysis. If you run a blind analysis, well, analysis will be completed. And if you go to results, diagrams for members, and you go to reactions and hit the FZ at least, and say descriptions apply, you can see that you get exactly the reactions you seem to be predicting. You can see that the four central columns, all of them have 226.15 kilonewtons as reaction. So it's perfect symmetry, as you can see. This is expected because our structure was symmetric. Also, I just ran the analysis blindly. If you go to results reactions, you can see those reactions. You can see that, for example, you have 92.43 multiple times. You have those central columns. Everything seems to be perfect. There are some minor differences, but I think for the purposes of the accuracy of finite element methods, this is perfect. Now, the summation of reaction is 1,800. Why is that? The reason behind this is because, well, this is the summation of values for loads. This is summation of, sorry, this is the summation of forces. This is summation of reactions, and the check here, this is the first time I open this, the check here is 0.00, which means that, well, the stability has been achieved. The 1,800 is basically 10 multiplied by the area of the slab. I think the area of the slab was, let me just remind you, 15 multiplied by 12, so 15, 150, yeah, 180 meters square multiplied by 10 is 1,800. Perfect. Now this mesh is a beauty. This mesh is perfect. There is nothing to be added to it. This is a perfection mesh. What does it mean to have a perfect mesh? Well, let me explain. Now this is really technical, and I don't want to start like talking finite element stuff. I might be giving a video series on that. But the idea is that plates are being discretized into smaller pieces that are your calculation units in the finite element method. Now, those little pieces are mapped to a benchmark piece. Now, this is like are actually the now for the master science and the PhD guys, you know this under the name of isoparametric calculation or isoparametric elements. You map the element that you have here onto the element that is a reference element. Now, let's say we have an element here. This is a rectangular element. This is the x-axis, and this is the y-axis. Now, from those, you can see that this has the dimensions of 1 and 1. And I think I found even this reference that can help you, but maybe I need to explain it with drawings. You have an isoparametric that has 1, 1 in x and y. This is negative 1 and 1. Those are basically coordinates. Negative 1, negative 1. And you have here 1, -1. Those are the XY components of your reference element. Now, your elements in the finite element mesh are not going to be rectangle. If they are rectangle, then they are perfect. But if they are not rectangle, for example, if you have this, let's say, some strange element like this, which will happen, if you have this element, then this is not a rectangle and needs to be mapped into the isoparametric element. Now, what does mapping mean? Imagine I have a laser pointer. Imagine that I hold in my hand a laser pointer that points with laser, basically. So let's put a point here on this element, laser pointer number 1, a point here in a different color on this element, and a point here in the center of gravity of this element with a different color, and a point here, let's say, and a point, for example, here. Now, those points do have, of course, moment values, because you remember those maps are actually color coded. Now, please notice that it's much easier for us to calculate everything related to stiffness for this simple element because of the convenience of its coordinates and the convenience of its shape functions. This is something really technical. I don't want really to dive into finite element right now, but I want to give you enough, basically enough knowledge to be able to understand that the element on the left is actually much easier than the element on the right in terms of calculating stiffness. As a matter of fact, the element on the right is a nightmare. Now, how do I calculate stiffness? I need to map. There's something called mapping. I need to map this element to this element. Now, obviously, this element per se doesn't fit your rectangular element, so the mapping needs to account for that. So, to understand mapping, let's go back to our points. So, where would the red point be on my mapped element? It would be somewhere here. Where would be this element be mapped on my perfect element? It would be somewhere here. Where is this element mapped on my perfect element? It should be somewhere here. Where is this element mapped on my element? I think it should be somewhere here. You see the distortion. Where is this element mapped on my element? I think this should be here. So the isoparametric formulation or the isoparametric concept of finite element maps a distorted element into a perfect element for stiffness calculations. This mapping means 3 things or more, but I just want to say 3 things. The first thing is there is a scaling in X happening. This could be, for example, 5 units long, and you have a 2-unit long element, so there is scaling in X. Furthermore, there is scaling in Y, because this might be 3 elements or 3 units in Y, and this is 2 units in Y. You need to scale that. Also, there is skewing. And to understand this, here are some helper lines. Allow me to draw a helper lines. So I will draw helper lines. So you see, the more distortion you have here, the more of a dystopia you get for an isoparametric element. This gets even worse the more distortions you have. For example, take a look at this element. Like, this is the worst. This is one of the worst elements you can get. Like, for example, this, or for example, this. Now, those are still possible, but of course inaccurate. And even if you have this kind of element, where you have this sort of stuff happening, this is of course unacceptable. This will even fail the calculation for an element because you have negative scalings. Like, all those elements, the more rectangular they are, the better they are for the isoparametric formulation. Now, will you always be able to do this? The answer is no. For the most cases, you will not be able to get perfectly rectangular elements, and Autodesk Robot will try its best. And that's why I love Autodesk Robot, because it has a very sophisticated measure. It will try its best to create to you uniform elements that actually try to be both as rectangular as possible and basically working as good as possible. Autodesk Robot is perfect in this regard. It tries its best to basically find those meshes. So the first thing I want to discuss is something about, now I'm trying to remember all the comments I got in the comment section. So the first thing was about aspect ratio. It is the ratio between the length and the width. And of course, the more aspect ratio you have, like if the aspect ratio is not 1, for example, if you have this element, which is an abomination of an element, this is a very bad element because suddenly you need to heavily modify it to get back to the isoparametric element. And by heavily modifying means that in one case you would just multiply by 2, for example. In another case you would divide by 5. This is a huge aspect ratio that doesn't work. Now, to deal with this issue, you would basically have to subdivide this into pieces that seem to be more friendly to the isoparametric element. Now, by the way, there is also an isoparametric element for a triangle. I don't want to bother you with this, but very quickly, the isoparametric element of a triangle, amongst other, is a right angle triangle. You can distribute this to find a better aspect ratio. And Robot does allow you to see this. Robot gives you those tools, and I will show you those tools today. Now, about triangles versus quads, I want you to understand that quads are much better than triangles, but quads do have more calculation tool. So here is the maps. Okay. Now I will turn off any smoothing. I don't want any smoothing now. Just turn off the smoothing because I wanted to show you the finite element itself. If I go to shear and go show the shear force, you can see that each element, okay, let me show the elements with FE mesh. You can see that each element has the ability to show a linear shear mapping, each element on its own. A rectangle or a quad is much better than a triangle because it captures shears better than triangles. But of course, it comes with calculation cost because a rectangle has 6 degrees of freedom in each joint or point. So you have 1, 2, 3, 4. Those are 24 equations. Whereas a quad has 18 equations. This scales quickly. Now, of course, I removed smoothing because I want to get the raw values of the finite element. For the moment, you will see, of course, a somewhat double linear equation. You can see basically a diagonal here. As you can see, there is a diagonal here. You have a linear increase here and a linear increase here. Some of you like to call this a parabola, but I disagree. So, of course, we are talking no smoothing now. And notice, without smoothing, the finite element mesh still looks cool. Now let's check out the triangle, how it looks like. So I go to job preferences, or I even can go here in mesh and go to mesh preferences, and I can access this from here, or I can go to job preferences and meshing, and then I can access the same thing here by going to this 3 dots, which gives you more, as you can see here. Now I'll just access it from here. Mesh options, and let's take a look. So I want to modify this. I want him to use 3 node triangles everywhere, whatever happens here. So I will force it now. Okay, and I'll just go to Delaunay. Okay, now sometimes Robot doesn't want that, but I'll just try my best to make it. So let's take a look. It doesn't. Okay, it doesn't want that. Yeah, okay. So it tried to give you some triangles, but it still tries to something called consolidate the mesh. If it sees triangles, it tries to consolidate the mesh to rectangles. Allow me to show you what happens if you add triangles. So if you go now back to shear force and remove all smoothings because you want the true values, let's calculate again. So take a look on the triangles. Triangles, let's go to detailed. So triangles do actually have the ability to mimic shear and linear, but if you go to moments, it only has one dimension of moment. You see, in a quad, you can have some sort of double linearity. Here you have only one dimension, one direction of moment. Let me show you what I mean. I hope I can find me yeah, there we go. Look the difference between what you see in a triangle versus what you see in a rectangle. You can see in a rectangle that there is a clear diagonal. There is a diagonal, as you can see, and there is like one equation for this surface and another equation for this surface. Whereas in a rectangle, there is no diagonal here. It's just one equation like this. Now this causes some problems in the calculation. You can see it here. For example, here you have red, which means negative moment, steel top, and then you have here blue, and then it jumps back to red. So this is a dystopia and discontinuity. To show this kind of dystopia and why this is a problem, you can go here and basically cut this element. And you can see that this is much worse than when it was a quad. So this is just the triangle versus quad discussion. Now sometimes triangles are required, but Robot will try to add quads whenever it is able. Now to show you this kind of dystopia, let me show you the panel cut. I think I'm showing MX, so I just cut near this dystopic thing. So, oh, there we go. Yes, exactly. That's what I wanted to see. Now let's double check if it shows me. Okay, let's go to detail. It shows no smoothing. This is perfect. And you can see all kinds of problems when no smoothing is activated. You can see this kind of squiggly jumping around because triangles are weaker than rectangles. So if you go back now to my meshing settings and just delete everything, I will keep the panel cut and I'll go to mesh options, and now I'll just use basically automatic and just advanced and just not force anything. Just use for quadrilaterals, use triangles for triangles, don't force anything, just recommend it, okay? And let's run the analysis again. You get back this. So when you select no smoothing, basically, after the analysis is complete, you can see that the rectangles are actually much better when compared to triangles because of the ability to capture a two-way moment. You see, there is like it's like one rectangle is a double triangle. It has the benefits of being a double triangle without having all 6 points, because you can actually consider one rectangle to be a double triangle and use only 4 points. So you get the best of both worlds. Now, this is the idea of rectangle versus triangle. You should use rectangle whenever possible. Now, what about another point that I wanted to talk about? Meshing improvers. Now, in some cases, you might be interested in just modifying your mesh. Robot gives you the ability to modify your mesh. It's not always the case to use, but you can modify the mesh using those modifiers. If you select mesh consolidation, this is what happens by Robot. It will basically try to merge things from being semi-rectangle to being rectangle. And it depends how much you are sensitive to consolidation. If you go to -1, you see, it tries to give you some graphical hints here. The more you go, the worse it becomes in consolidation. It becomes less flexible. Here you are basically trying to consolidate only the most square-like of figures. If you go in the middle point, you are actually allowing some rectangles, but those shapes are not consolidated. Of course, if you go more, then, well, you are in the absolute dystopia now, because you will only allow things that do not violate the finite element method. This violates the finite element method, and this violates the finite element method. So, of course, that's a no-no, and it will never be a green light, by the way. But, well, I mean, you can just consolidate this if you want. I don't, because I don't need to. You can also check the mesh quality. For example, if you basically select the panel here and click apply, now nothing is highlighted because the quality is above half. Now, if you go to a quality to 0.8, nothing will be highlighted because everything is above 0.8. Now, if you go to 1, this is impossible, so everything is highlighted because everything is either equal or less to 1. You need this sometimes as a quality measurement. Whenever you have a mesh that seems to be not really good, and you can check out where the problems are. Now, if the problems are above a hotspot, and by hotspot I mean a rapid change in something, like for example, if you go to maps, let me show you what a hotspot means with smoothing now. You see, above the columns, you have above the column, you have rapid changes in both shear and moment. Those are hotspots, and your mesh quality should be good at those hotspots. And sometimes even your mesh fineness might increase or decrease. I mean, I never talked about this, I know, but well, now it's the time. Usually in meshing, and this is a move I wanted to understand, when I'm still building my model, I go for cost, because the only reason I'm doing this is just to see if things make sense. Once you are in the final stages, you could just go to fine and just find your mesh. But for now, I'll just use my cost mesh and keep it as it is. So, okay, what else do I have for mesh abilities? I can basically, instead of mesh quality, I can also mesh refine it. So if I feel, for example, that this element is too big, I need to refine it, well, you can select the element like this, and this goes on an element by element basis. You can select elements, not panel, elements, finite elements. It selects finite elements. Allow me to explain. Let's say we want to refine this region, and I click on that, and I want to refine it. You can refine it as a single refinement or as a double refinement, a triple refinement. You are breaking it down into multiple elements. Now, a simple refinement doesn't cause any change in the adjacent neighbors. Allow me to show you. If you click OK, of course, now it basically destroyed my model. I need to calculate again. You see, this element got refined with 4 triangles, which costs more, but the adjacent elements need not to be changed. That's why it's called simple refinement. If you go to double refinement, the adjacent elements need to be changed. Allow me to explain. If you select this, this means that it will break a point here. If you have a point here, then it must be connected. It just cannot be a point on the middle of an element. Allow me to show you. If you click yes, of course it destroys the mesh. I need to calculate again. And you can see that the adjacent elements got affected because you chose to break it down. Then the adjacent elements need to be affected. This is different than the simple mesh. Of course, it gets worse, and not worse and worse. Of course, it gets more extreme when you try to break down into triple. For example, like this. I'll apply that. Yes? And now you need to calculate again. Now the things get affected even more. And you can see this. Now, this is called like adaptive mesh refinement. Now, this is not what we would do. The average user on Robot doesn't do that. The average user just goes to, and this is, by the way, by the average user, that's good enough for structural analysis purposes. We're not doing research here. But the average user goes here and just selects his mesh fineness and goes with his life. And if he wants to modify, maybe he changes the element size and everything is fine. Let me, first of all, delete the mesh. Everything deleted now, and let's run the analysis again. So it should refer back to its original mesh, and you can see everything is fine. Now notice when you delete the mesh, you delete everything you have done before. But if you don't delete the mesh, the refinements stay when you calculate again. Now, when you have a point load on an area, the stress is infinity and the moment should be infinity. You don't get moment infinity because there is stiffness involved that is too deep to be talking about. But you see that the moment doesn't go to infinity. The crazy part here is that if you change the mesh size, let's just choose a mesh size of 0.1 and hit OK button. And let's run the analysis again. The moment value changes. Okay, now notice what happened here when I just changed the mesh. Of course, first of all, I'm overloaded with mesh, so let me remove the mesh now. Now it's very fine. It's extremely fine. But the moment values have changed. You have 242 kilonewtons per meter strip, of moment. Why? What's the idea? If you go here, that's not the case. Like, where is the moment here? Now, to understand where the moment is, I need to show the values. So let's go with descriptions and click apply. And you can see the moment value being exactly on top of one. Okay, I'm regretting this now. My computer is breaking apart. But you can see the moment value being exactly here. And this is odd. Why? It is odd because the distance is just almost zero. Like, look, let me show you the finite limit mesh. Yeah. Notice this burning levels of stress happens only at 5 centimeters because, I mean, 0.1 was our mesh size. So this is something that you don't even need to consider. This is, for me, a numerical problem in the finite element, which is absolutely strange because, like, the normal sense says that if you want to have a better finite element mesh, then make it smaller. Yes, that is true, but there is a limit for how much smaller you will make things. If you make them too small, then you reach something like, I don't know, you reach a position. Let me just remesh this thing because I think I'm messing up. You reach a position where you are magnifying the stresses because now, with smaller finite elements, your area becomes smaller, which will basically change some of the stress calculations and you will get crazy moments. So I think I've talked about this before. And to try to explain what I talked about before, I said that if you have a finite element mesh and you have a moment on top of a column, then you should not basically take the top of the column tip as your moment. Maybe you want to just move away 5 centimeters or something just to get reasonable results. Now, how do you detect if you are going into a numerical singularity or a problem with your finite element mesh? You can easily detect this by looking at the region where the stress is burning. When it's a bigger region, then you say, okay, I don't have a stress, I don't have moment concentrations because the finite element, I have actual moment concentrations. And of course, if you make the finite element smaller, you will start getting stress concentrations. This is strange, but it is what it is. Now, I might be talking later about I need to make sure if it works or not. I think there is a chance to make this column have an area on the slab to kind of remedy the problem of having this little needle on the slab. But of course, I need to dig it out and present it to you later. Now, what about emitters? I might think about this for later. This is something that is not usually used, but you might want to have emitters around edges of stresses, and it basically tries to create circles around that point to try to mesh that point as much as possible. And once again, this is one of the points where you have infinite stresses because of corner. So emitters do help you with that. Now that's one thing. The second issue I had was from our subscriber Donald Khanye, who mentioned that oddly, if the mesh is not 100% symmetric, the reactions are different if the mesh is not symmetric. Allow me to show you. If you go to reactions now, you can see that the reactions are symmetric. At least we're looking at those four. If the mesh is unsymmetric, the reactions are different. And that's 100% okay. This is absolutely okay and within the realm of finite element. Allow me to show you. Let's delete everything here. And let's go to geometry, nodes, and let's just add some random nodes here. Just now I added, as you can see, some nodes. They are just random. And let's run the analysis. Now, if you run the analysis, try to mesh those nodes. Let's challenge it even more by basically targeting some strange points like this. Let's run the analysis again. So now I think there are some, yeah, see, there is some messed up stuff happening here. Now, this is going to change the result, believe it or not. The results, for actions at least, and for everything else. What happens here is that you don't have any symmetry. I know from a human standpoint, you have perfect symmetry. You have one plate with columns being symmetrically placed. But if you look on the mesh and the stiffness matrix, those are not symmetric. And as a matter of fact, you might have problems here. I mean, let me check very quickly the mesh quality. And if you go to 8, yeah, you see now you have problems here. Those are problems. So you can see the quality being a little bit less for those elements. And my point still stands that the reactions now will be different. And this is perfectly fine. But let's take a look. Where is it? Reactions. Yeah, you see, now we have slight differences in the reactions. The last point that I was asking about is about shear locking. I think I need to show this to you in another video because I want to try to make this video as user-friendly as possible. Maybe I will start my scientific lecture videos later, where I will be talking about the finite element method as a concept. One final thing I want to talk about is robots' ridiculously overpowered mesher. Now, me being a programmer, I have been with mesh generation. I've been personally dealing with mesh generation, and I tell you, it is not a joke. Now, by the way, I deleted those extra points I added because I want to go back to my normal mesh. The mesh generation is not a joke. What I mean by this? I mean that when you mesh, this beam needs to be cut into pieces. I don't have a beam, right? Any beam that passes through this slab must be connected by the slabs at the nodes. Allow me to show you what happens if I just draw me a beam lazily like this. I'm just drawing a beam. Now this is incorrect. This mesh now is incorrect because you can see at the intersection points at the intersection points between the beam and the elements there are no nodes. This doesn't work like that. Now of course there are no nodes because I have not yet calculated. If you calculate now, you can see how ridiculously overpowered an OP Morbot's mesher is. It just weaves the mesh around the line. Of course, here you have problems because you have a shallow angle here. This is totally normal. This is inevitable. And there is research talking about NURBS, NURBS, in finite element, but I will just leave it for here. And this mesh is so powerful that it understands connections between plates and plates. I just love it. I just love it for what it is. So I'm going to show you. If you go to basically, I don't know, like shell, and just draw something non-horizontal from here to here, it detects that, and when you mesh it again, this is a horrible nightmare to mesh, to be honest. But if you mesh it, it just weaves it around itself. This is amazing and really powerful, and just let me show you something very cool here. So what happens if you penetrate this wall? It will actually mesh around the point of penetration. If you click here to here, this is, wait, no horizontal beam. If you click here from here, I just defined me a beam that is in space. So what robot does is it calculates the spatial intersection and then weaves a point around it. Let me show you. If you run the analysis, trust me, I have done this in Strado, my software, and it was not a joke. Wait, what? It didn't find it? Huh. That's surprising. It's a failure in meshing. It should not be like that. No, that's... Well, I guess I found a point where I am doing better than this. It should have... That's strange. I'm surprised. It should... This is now incorrect, by the way, the mesh, because you have an element here, as you can see here, and it doesn't connect with this element, meaning that the beam doesn't feel the wall here, and the wall doesn't feel the beam. There is no force exchange between them. So what I'm trying to say is a mesh in a finite element software is basically the skeleton upon which you are moving the forces. If you have two things connected in a mesh at a node, this means that they can see each other and that they can feel each other. If you don't have that, then they don't see each other, don't feel each other, don't care even about each other. and it's very important that you do have a consistent mesh. Now, one of the mistakes one could do in a finite element analysis is to do something like this, like just barely make a mistake in drawing and just do this. I'm drawing me a thing here. I'm drawing me a plate here, but messing up something, as you can see. Yes. Now, this little detail here will cause all kinds of problems, at least in Robot when I was like in 2000. Robot 2010 didn't have the ability to mesh this. Let's check out if Robot 2017 does. It does. Oh, okay, wait, it corrected it. Okay, let's go on a... I'm surprised, to be honest. It just corrected it, I guess. Okay, let's make it even harder. I want to try make it fail. I want to try it not be able to consolidate the mesh to show you how a bad mesh looks like. So let's click here. Let's make it like this. Let's try make robot suffer. If it doesn't suffer, then they have modified the mesher. This would be a surprise for me. But let's run the analysis and take a look. Yeah, overlap panels. Okay. Does it mesh? It does mesh, but it tells you overlap panel. Okay. Oh, yeah. Here. That's what I'm looking for. This is exactly what I'm looking for. Now, back in the day in Robot 2010, we had a very quick idea to understand where things can go wrong whenever I have overlapping panels. Whenever you have overlapping panels, you will see suddenly an abomination of points because Robot tries to weave those points together as best as it can and ends up with a plethora of points here, which will immediately direct you to a problem in your mesh that you have overlapping panels. And the easiest way is just to delete the panel. First of all, delete the mesh. And second of all, delete the panel and just draw it again, basically. Now, if you run the analysis again, it should be working. It will delete the nodes that were crazily added and gets back to its original thing. Notice this is a bad element, to be honest. I don't like that. All those elements are bad. What I would be doing is I might even distribute them or something. But remember, it was due to the fact that I just drew me a line. So yeah, I think that's everything I wanted to talk about in meshes. I hope that you have a appreciation of the different tools here. Of course, I am here only to give you. I try to give you some like food for thought. Of course, you need to investigate, especially here. You might need to investigate more details about what kind of elements you can choose, how Delaunay and Kang's algorithm works. This is a little bit too technical, but of course, feel free to tell me in the comments if you want to have a second part for this. But of course, this will be done. The second part for this, the advanced meshing options, might be covered in a different video because today I wanted to cover the practical issues about meshes. Maybe the advanced meshing ideas will be covered later because I want to try to keep this slab series, at least for now, as a practical series. For later, I will just give me a deep dive into the meshing and maybe talk to interested minds about all what it means to have here. It's a lot, to be honest, and it needs to be basically talked about. So just to give you a taste of what is to come, I would be talking sometimes about Delaunay. Now, what is Delaunay? Delaunay is a triangulation method that triangulates a plate to a certain maximum area of triangle and a maximum and a minimum angle of that triangle to basically be able to produce good triangulations. This Delaunay triangulation is usually used in mesh generation, even in mesh when you have, for example, in Autodesk Civil 3D, when you have ground data of a total station or level and you want to mesh to approximate and interpolate the intermediate values. It's kind of a cool concept where it basically tries to triangulate an element as much as possible, as good as possible, and actually is even used sometimes to create something called the Voronoi diagram. This is a lot of details I will be talking about in my deep dive. For now, I'll just leave it as is. Of course, this triangulation now here is an abomination. You can modify it and improve it by adding constraints to this triangulation. For example, one constraint is to constrain the minimum angle. The angle should be, for example, more than 30 degrees. Well, this is maybe a talk for later. I mean, take a look. This is an abomination, and this is actually better. The same points are used in a bad Delaunay triangulation, which has absolutely an abomination of elements, and a good Delaunay triangulation, which is a constraint Delaunay triangulation. Well, that's everything I wanted to talk about. I hope that you have enjoyed the video. Of course, if you have enjoyed the video, then please like, share, comment, subscribe, especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video.